Hello, I'm Sebastian. Welcome to 9 Trees podcast. Today, I will summarize and review the book. Quantum Physics in Minutes by Gemma Lavender is a compact, highly accessible guide to one of the most counterintuitive areas of modern science. Designed for curious readers who want the big ideas without heavy mathematics, it organizes core concepts into short, digestible segments that can be read in quick bursts. The book introduces how quantum theory emerged from attempts to explain phenomena classical physics could not, then moves through the principles that now underpin much of contemporary technology and research. Readers can expect clear explanations of particles and waves, uncertainty, probability, and the strange ways measurement shapes what can be known. Along the way, it connects abstract ideas to familiar outcomes such as semiconductors and lasers, helping the reader understand why quantum physics matters beyond the classroom. The result is a fast-paced overview that builds intuition, corrects common misconceptions, and offers a grounded starting point for deeper study. I will give you key takeaways from this book. Firstly, from classical limits to quantum beginnings, a central theme in introductory quantum learning is why classical physics had to be revised, and the book frames quantum theory as a practical response to stubborn experimental puzzles. It traces the shift from deterministic, continuous models to a world where energy exchange appears in discrete packets and where classical intuition fails at small scales. Key early milestones typically include attempts to explain blackbody radiation, the photoelectric effect, and atomic spectra, each pointing to quantization and the need for a new framework. The value of this topic is not just historical, it helps readers see quantum physics as a disciplined theory built from evidence rather than as a collection of weird anecdotes. By understanding what classical models predicted and how experiments disagreed, the reader gains a reasoned foundation for later ideas like wave functions and probability. This approach also clarifies a frequent misconception: quantum behavior is not optional strangeness. It is the consistent rule set required to describe nature, when matter and light interact at tiny scales. The book's short format supports this narrative by breaking the origin story into bite-sized steps that accumulate into a coherent motivation for quantum mechanics. Secondly, wave-particle duality and the language of quantum states, Quantum Physics in Minutes, emphasizes the conceptual bridge between particles and waves, showing how quantum objects can display either kind of behavior depending on how they are probed. This topic typically introduces matter waves and the idea that electrons and photons are not neatly categorized as one thing or the other. Instead, quantum theory uses a state description that encodes possible outcomes and their likelihoods. Readers are guided toward an understanding that a quantum state is not a hidden classical trajectory, but a mathematical representation of what can be predicted. Without diving deeply into equations, the book can still convey why interference patterns matter and why they imply a wave-like aspect even for individual particles. This lays the groundwork for grasping why quantum predictions are inherently probabilistic and why experiments like double-slit setups are so pivotal in popular explanations. The payoff is practical intuition. When you hear that quantum objects behave like waves, it does not mean they are smeared billiard balls. It means their state can combine possibilities and produce interference. That insight becomes essential for later topics such as measurement, uncertainty, and superposition. Thirdly, uncertainty, probability, and what measurement means. A major stumbling block for newcomers is the role of measurement, and the book addresses it by tying uncertainty and probability to the structure of quantum theory rather than to experimental clumsiness. The uncertainty principle is commonly presented as a statement about pairs of properties, such as position and momentum, that cannot both be sharply defined within a single quantum state. This topic helps readers replace the myth that uncertainty is merely about limited instruments with the more accurate idea that quantum states impose fundamental limits on simultaneous definiteness. The discussion also situates probability at the heart of prediction. Quantum mechanics does not usually forecast a single outcome, but a distribution of outcomes with calculable likelihoods. Measurement then becomes the process that yields one realized result from those possibilities, updating what is known about the system. By approaching measurement as a rule-governed transformation in the description rather than as mystical observer influence, the book can keep the explanation grounded while still acknowledging interpretive debates. Readers come away better equipped to understand why quantum theory is extraordinarily precise in practice, even though it speaks in probabilities, and why the act of observing is inseparable from how quantum properties are defined. Fourthly, superposition, entanglement, and non-classical correlations. The book highlights the most distinctive quantum features, especially superposition and entanglement, because they explain both the fascination and the real power of quantum theory. Superposition refers to a state that combines multiple possibilities in a way that can produce interference, not merely a lack of knowledge about which option is true. This idea becomes more striking when extended to entanglement, where two or more particles share a joint state so that outcomes are correlated beyond what classical models allow. The crucial point is that entanglement links predictions about combined systems, even when each part individually looks random. Introductory accounts often mention the challenge entanglement poses to classical intuitions about locality and separability, while also stressing that it does not enable simple faster-than-light messaging. By keeping the emphasis on correlations, tests, and experimentally verified behavior, the book can introduce these ideas without sensationalism. This topic also acts as a bridge to modern applications. Many emerging technologies, from quantum cryptography to certain quantum computing approaches, rely on superposition and entanglement as resources. Readers gain an appreciation of why these concepts are not optional curiosities, but central pillars of current quantum science. Lastly, quantum physics in the real world and modern frontiers. A concise guide benefits from demonstrating why quantum mechanics matters in everyday life, and this topic connects foundational principles to widely used technologies and current research directions. Even without technical detail, it can show how quantized energy levels explain the behavior of atoms and materials, leading to practical consequences in electronics, imaging, and communications. Semiconductors and transistors rely on quantum band structure. Lasers depend on stimulated emission and discrete transitions, and magnetic resonance techniques draw on quantum properties of spins. These examples reinforce that quantum mechanics is not confined to exotic laboratories. It quietly governs the devices that define modern society. The topic also gestures toward frontiers that have popular attention, such as quantum computing, quantum sensing, and quantum secure communication, clarifying the conceptual ingredients each depends on and the challenges that remain. By framing applications as extensions of the core ideas already introduced, the book helps readers integrate what might otherwise feel like disconnected facts. The overall effect is to turn abstract principles into concrete relevance, motivating further learning and helping readers evaluate headlines about quantum breakthroughs with more informed skepticism and curiosity. In conclusion, Quantum Physics in Minutes suits readers who are curious about how the universe works but do not want to start with dense mathematics or a full-length textbook. It is a strong fit for general science enthusiasts, students looking for a refresher before a course, and professionals in tech or engineering who want a clearer sense of the principles behind modern devices. The main benefit is intellectual leverage. The book helps you build a coherent mental model of quantization, probability, measurement, and non-classical correlations so that quantum ideas stop sounding like disconnected paradoxes. That improved intuition can enrich everyday life by making common technologies more understandable and by sharpening your ability to assess popular claims about quantum computing, entanglement, or the limits of knowledge. Compared with many similar introductions, its advantage is speed and structure. Short, focused sections reduce intimidation, keep momentum, and encourage rereading, which is often necessary for topics that challenge intuition. If you want a compact purchase that delivers the essential vocabulary and concepts without heavy prerequisites, this book provides high value as a practical starting point and a reliable map for deeper exploration. If you would like to support Gemma Lavender, you can buy the book through the Amazon link I've provided in the podcast description. After reading the book, please let me know what you think and share your thoughts. See you around.